Great pleasure to have Aude Billard give today's final talk before the poster session. Aude is leading the LASA laboratory at EPFL, focusing on robotics. Let's have you here. Take it away, Aude. Thank you.
Sure. Thanks a lot for the invitation. I understand my talk is going to be very different from what we've heard today. So I'll try to make it as any roboticist, something a little fun to look at. So there are going to be videos. So be reassured, but not just videos. We do use machine learning in robotics. There are different ways of doing it. I like first to motivate why we're doing it in my group in particular, because we tend to be more control oriented, so more theoretical. But then lately we've faced that there are a number of things that you cannot explicitly write. And as an example, this is a typical thing that is very difficult to. Okay, I think you checked that the video we're playing. I had to ask for this to be checked before.
Switch from presentation mode. The screen show the presentation mode.
Otherwise, I'm just gonna take my laptop.
Yes, if you're sure.
But just so you haven't tested them.
Yes, but in the presentation mode, I think it works.
So why don't I go there? It's not embedded.
Otherwise, you just stand like this, and
Non, attendez, parce que j'ai plein de choses qui tournent en même temps. All right, yeah, here you go. Yeah. All right. I would have been very surprised if the videos were working. Usually they don't work if you give the slides to another presentation. So why is this problem difficult? This problem is particularly difficult because the bottle is filled with water and you don't exactly know what amount of water there is. And it's extremely, I mean, there is no way that you can actually really write explicitly how the water is going to be displaced as the bottle flies. So there is room for data learning here typically, but you still need to have control. You still need to have some guarantee that you're going to actually reach the bottle with the right position and the right orientation. So you have to think of this as ordinary differential equation, which we would code as dynamical system with a fixed point, which is in position orientation. But then we're going to use machine learning as a way to shape the particular functional that we want to preserve properties. For today, I decided to focus on one particular problematic that we looked at, which was to be able to have those functional that switch across different different attractors, so different fixed points in space. So imagine that you want to pick up this object and it's falling, and you have two different places where you can catch it. You can catch it at the top or you can catch it at the neck. Those are two different fixed points in joint space, because in one case you have to close very tightly your finger just to grab it at the neck, or you have to have a more open grasp. And you have milliseconds to take this decision. So it's clear that there is no way that you can plan and you can run a nice optimization, even if it's finite in time. I'm sorry to say, but there is no time on Earth, especially in a robot. So the best for us is when it's what we call closed form, analytical solution, in which case all you have to do is to compute the analytical solution. And usually it's just a product of matrices and multiplied by vectors. So it's quite fast. So the first problem we looked at was if we wanted to be able to switch across two systems, what we need is to learn two different dynamics, which I illustrate very simply like this. Imagine that you have one dynamics on the left-hand side, which here is two-dimensional, but of course for us it's much higher dimensional, with a single fixed point, which is this particular orientation and position on the glass on top. And then if anything changes, then you want to have to switch immediately to this other functional here, which has another set of fixed points. And you have a boundary in between. So from a machine learning viewpoint, you immediately think classification, but you also think classification and regression. Why regression? Because typically you want also to model the dynamics here and to make sure that the dynamics on either side vanishes and has fixed point at the right hand side. So one natural way of approaching this problem, we thought at the time, was to use the support vector machine framework. And I apologize for the mathematician in the room because I did not formally explain all the details. I assume that the machine learning folks will follow me. So I'll be a little more specific here. Support vector machine, as you know, is usually a binary classification, and it outputs +1 for one class, -1 for the other class. But actually, to do that, it takes a decision. It takes the sign as a decision to decide if it belongs to the +1 or minus classes, take a decision on the sign of a continuous function, which here on purpose I write v of x. It's a continuous function. It's actually positive everywhere, and it becomes 0 at some point, which is not necessarily predefined. So usually it's 0 exactly at the classifier boundary, which is this boundary here. And then it's negative on the left-hand side and then positive on the other side. And we can even show that this is an infinite number of hyperplanes that all move away from the boundary. So at the time we thought, well, this is, if I just look at the left-hand side, I have a natural Lyapunov function. It's something that, that will decrease and eventually vanish at a point where I'm interested in. So if I do that, the problem is that if I train with traditional support vector machine framework, the system will vanish, not necessarily where I want, and not necessarily at the point where I want it to vanish. But support vector machine is also used for regression, and you can also rephrase the same problem, the same optimization with different constraints as a regression problem. So what we thought of doing is simply to combine the two and to do an augmented SVM, where you solve basically for both classification and regression at once. So it's not very, I mean, it's quite intuitive, in fact. You will start, if for those of you who are familiar with this problem, this is the way it works. So I'll just go with it. So the first line on top is the traditional minimization that you have in support vector machine. Norm of W represent the hyperplane in high dimension in the feature space. You're minimizing for the norm of the hyperplane plus some cost for the slack variable. And the traditional constraints from support vector machine are highlighted in yellow. The first one simply requires that all the data points on the left-hand side, right-hand side of the hyperplane lives on both sides with potentially some slack, and the slack variable needs to be strictly positive. But if you want to have both worlds, that means you want to classify correctly the two dynamics, and you want also that all the data points follow the dynamics and have a single attractor point and vanish, we augmented that by adding more constraints. So this constraint, for instance, here, take the Jacobian over xi times xi dot, which represent the velocity. In other words, what it's requesting is that now we actually follow the dynamics. We follow the velocity. So not only do we want to classify the data points in the right, on the correct side of the hyperplane, but we also want these data points to follow the flow, to go that the gradient follows the flow. And then finally, we have to force the flow to vanish at a specific point, and that's the attractor. So we need to force, in fact, the kernel, the sum of the kernel to vanish at that particular point. But you can set this as a set of constraints. They're explicit constraints. And the nice thing also is that all of this remains a convex optimization. Nice. So you have a bit of both worlds. So if I look then at the final equation that we get, the decision function, because with support vector machine, you get a decision that allows you at runtime in closed form to decide if you're going to move on the left-hand side or right-hand side of the hyperplane. In other words, if you're going to reach with the big grasp or the small grasp, for the example I showed you before. This decision function has this equation. I'm going to go through each of the terms separately. The first one is the standard SVM. So for those of you who are familiar with this linear combination, alpha I are scalars, yi are just the +1, -1, so this is the decision, and then k is the kernel, which usually is an RBF kernel applied on the data point. So this is the standard support vector. So if I take an example in 2D of a dynamics that I'm trying to represent with this decision function, and here I'm only looking at the effect of the decision function on one side of the hyperplane, the one that I can control for, which has this Lyapunov function. If I only apply the alpha support vector, which are illustrated as round points there, I get some dynamics, but as you can see here, it does converge to a 0 point, but not where I would like it to be. So the 0 point in this example, where is my mouse? Up. It's this pink arrow. Those are the data points, and this is the vector field, which is rendered by the traditional support vector machine. Now, when you solve, of course, because we've added more constraints, we have more Lagrange parameters, so we end up with other terms that we call the beta support vector. And if I illustrate the effect of this beta support vector, what they do is that they force to follow the dynamics. And this is the regression support vector. So they force to follow the dynamics as we see here. So they're these triangles. And as I add more and more of them, then I will follow more and more the dynamics. The third term on the right-hand side is a nonlinear bias. Gamma is again the Lagrange parameters for that last constraint that forced the system to vanish at a particular point. And here, of course, it takes the partial derivative of the kernel, which we can compute because the kernel is a continuous and at least C1 function. In our case, those are RBF functions, so they're in C infinite. And then finally, we have a constant bias, which we can use to change simply the level set of the function. So we can extend this easily for multi-class classification simply by taking the argmax. And at runtime, then we can run this on a real robot. So just for the fun, this is typically the experiment we can do. So at runtime in milliseconds, we can choose if we close on the grape, on the neck or at the bottom of the bottle. In this case, we have 0.2 seconds, so 200 milliseconds. It's extremely quick. For robotics, it's super quick. Why? Because even though we always think of robots as being fast, they're not that quick. So it's like the tennis player. By the time you compute, you already should be running if you want to catch the ball. So that's the necessity to compute this. What I wanted to talk about today is an extension of this work that we did recently. So when we used this support vector machine approach, we were doing hard partitioning. That means you really have to choose, and you can belong to only one of the two partitions, and you could split the space, but that was the space that you had at your disposal. Now, this exact partitioning of the space was also a supervised learning problem. We needed to know how many classes we had. In other words, we needed to know how many dynamics there were. And we decided to move away from this because in robotics, there are many reasons sometimes to not know the label by definition. So first, I'm going to start by taking a dynamical system perspective to this problem and just illustrate with some very known dynamics that often dynamics may have different attractors, but they're completely intertwined in space. So it's not as easy classification problem as we will imagine. So this is an example for the Duffing oscillator. You have no clear partitioning of the space. As you can see, you can start from points that are very close to one another here in the state space, and with just a small epsilon on the left, on the right, hop, you diverge, and then you reach two different attractors. So if you feed that to a partitioning of the space, it's to a machine learning algorithm, it may be difficult to separate. Another thing is that we wanted to really be completely unsupervised, to say we don't know how many inherent subdynamics we have in our system. This is often very useful for us as roboticists because we don't quite know in advance whether when you get demonstration in the field, if you need to segment this different action in 5 or 10 or 15 different subactions. So we wanted to discover both the dynamics, the number of those dynamics, their shape, as well as their attractors. This is a completely unsupervised learning problem. We know neither how many dynamics we have, nor the shape. What I mean by the shape is the actual functional for each of those and where the attractors are. So imagine that you have a bunch of data points, and I write here capital X as the matrices in which column-wise I'm going to put all my data points, and my data points consist of all the position and the associated velocities. Imagine that this is given to you. It can be given to you by a human making a demonstration. We often use optimal control where we solve for feasibility, so optimization, but first to train the system and then to have it in closed form. So we can generate this to make sure that we have kinematically and dynamically feasible dynamics for the robots. So we have these data points, but they're unlabeled, okay? We don't know. We just have a bunch of these position and velocity that are observed. So it's an unordered and unlabeled list from a machine learning viewpoint. And besides, again, notice that within the list, some of those data points may belong to one class or the other, and you just don't know. So you cannot use a closeness in space in the data point itself. So for this, we moved to something a little different, but you're probably familiar with this. We looked at graph theory, in particular manifold learning and spectral clustering. And thought, well, why don't we take this? Because the only information we have at our disposal is the fact that we know the velocity associated to each of the data points. And this velocity vector is in fact inherent to the dynamics that is inherent to each of these this part of the field. So let's build a graph to connect the points, but a graph that is informed as much as it can be. That means it's informed only from the point of view of just one point. What the point sees, it's itself and its own velocity vector. And I can create a similarity measure, which will, and I'll explain how we build that. It's a new type of kernel that will decide if I connect or not the point. So I will read all the list of the data point that I have, and then I decide if my graph is, if the points are adjacent or not. And it's a very binary graph, very simple, 0, 1. So, if the similarity matrix is bigger than a threshold, then yes, they are connected. If not, they are not connected. So once we have this, we need to look at the actual kernel that we're going to use, this similarity metric. It's a very simple one. Take 2 points. The first thing that we want to look at is whether the points are close in Euclidean distance. So we take the classical approach. So we look if they're far, then the locality will be close to 0. If they're close, then it becomes 1. Then the other thing is that we're going to look at whether the velocity part of the data points align, if there is continuity. In other words, if the two dynamics are continuous, then obviously it's probably the same dynamics. And we want both directionality as well as continuity across a pair of points, because at some point the two dynamics will diverge. So we do that. So if they are connected, if they are pointing in the same direction, if they are not pointing in the same direction, then this would be much bigger than 0. If they point in the collinear, if you want, in space, then the directionality would be very close. So with this, the advantage is that if you use a simple RBF kernel and you were to connect the graph by using a traditional just positioning in space, what you will have is what you observe here, is that you will have a lot of spurious connection. So here in the diagonal, we have all that is nicely connected. All the points are nicely connected to one another, but then they're closely connected to points adjacent in space, which is not adjacent in the dynamics. And then we're going to have spurious attraction, like from these two dynamics that are very close to one another. So to get rid of this, with this velocity augmented kernel, we managed to remove, in fact, all of those spurious attractor and make sure that all the points of these dynamics are connected to one another, and all of those are connected to one another. And we can even do that for dynamics that are intersecting, so that you preserve, in fact, the directionality of the previous dynamics and be able to clean that up and have just a single connectivity. Now, for ease of reading of this graph, what we did is that we ordered the points. So that means we ordered all the points of this class and all the points of this class one after the other, so that we can better read out this matrix, because otherwise you cannot interpret the diagram. Now, we have, imagine that we have all those dynamics. We have this velocity kernel. We create the adjacent matrix. From this, we create the graph Laplacian, as is usual in graph theory. And then we do an eigen decomposition of the graph Laplacian. And we look at the eigenvalues, and it's been done for decades, and people know that they can use, this is the basis of spectral clustering, is that you can just look at the multiplicity of the eigenvalue 0. If it's completely disconnected, or if it's almost disconnected, it's close to 0, and then you can cut off and discover the number of clusters. With the velocity kernel, that allows us simply to discover the number of dynamics. So we've solved one problem. We know now how many dynamics we have. But the secondary problem now is to be able to make sure that those dynamics can be represented, because we have the problem of knowing what these dynamics are. So we started studying the eigenvectors for each subdynamics, and we observed one thing, is that if we take some specific eigenvalues for which there is an upper bound, which is fairly small eigenvalues, it turns out that there are k latent space that we can create, and in those k latent space, all the entries are monotonic. So in fact, when I looked at them, so the PhD student who worked on this observed that there was a monotonicity that was growing and decreasing, and then looking more at the mathematics, found that these are simply Chebyshev polynomials. So in fact, those are series of sinus and cosine. And if the eigenvalue and is proportional to the eigenvalue. So the eigenvalue, if it's small enough, then in fact, you embed one dynamics in one cycle of the Chebyshev. And that's why it's monotonic in that particular space. So the fact that it's monotonic is wonderful. Why? Because when we project into the latent space that is represented by these eigenvectors, our nonlinear dynamics originally becomes linear. And in the world of control theory, when you can make something nonlinear or linear, you jump of joy with joy, because then you can control it. So that was the marvelous thing, is that not only can we discover the number of dynamics, but we can also linearize in each of the latent space. And we know that we have as many latent space as we have dynamics. So we've discovered the dynamics. We can project in each of the latent space separately. Besides, also, each of the dynamics are projected into different latent space. That means that we separate the dynamics. And the other dynamics project to the point 0, to the origin of the system. So we really decompose the problem. So I'll give you just a small example. So this is a typical graph base that we've constructed. So you have here 4 branches. There is a cycle here, which we represent, because in robotics, we know that we never have perfect measurements. So often we simulate noise in terms of our measurement of where the attractor is. And the attractor is in around this small cycle. And this is the spectrum of the eigenvalue. And our bound says that any value of lambda which is below this lends us to the number of, first of all, well, here we use simply the fact that we have the multiplicity of the eigenvalue, which you don't see, which is 3, so it allows us to decompose that. But on top of that, we also discover that we have 3 eigenvalues that are quasi-equal, and those represent, in fact, the number of eigenvectors that we can use for the reconstruction. So if I use just a 2D latent space projection here, you see that these dynamics that I had before, when projected onto the latent space that correspond to the first 2 eigenvalue non-zero one here, is flat, and it's linear here. And I can also project it into 3D. In 3D, it's quasi-flat. It's not exactly flat, but it decreases with an order of n to the square, where n is the number of data points. So if you have many data points, then it's 1 over n to the square. So it's you can almost neglect this. Other example, so if you take this 2D system, which has clearly 2 different attractors, you generate data, you subsample trajectory, then you discover these 2 dynamics, and they live in 2 different spaces. So you have to understand that this is the blue space. So this is the blue space that corresponds to the first set of eigenvectors. This is the red space that corresponds to the second dynamics eigenvector. All of this is in closed form. So the only difficulty, in fact, is the kernel itself. Is that, of course, as usual, it depends a little bit on the threshold. So you have to choose well the threshold to decide when you're cutting and when you're not cutting the edge of the graph. But that's the only difficulty. Yeah, this is another example for the pendulum with friction and the Duffing oscillator. Now, how do we use this for control? Clearly, you send into a space which is the same dimension, so that's the good news, but then you need to go back. So the only way is to do a diffeomorphism, so we can learn this diffeomorphism. We did not invent anything. We use existing diffeomorphism for this. And so this is an example. You get different dynamics, which are represented here in 2D. Then you project. The projection are always the same, and they're always this linear projection. And then you can learn the inverse of the dynamics. We contrasted the fact that we use this particular latent space versus other latent space, and whether it buys us something. And yes, the advantage over doing, so there exists diffeomorphism using, so RANA, for instance, is using purely neural networks for back and forth. It's fairly heavy computationally. So of course, this method is lighter in the dimension in which we work because we can compute the Laplacian. Clearly, you go to very high dimension, this is disputable. But for us in robotics, we usually do not exceed 60 dimensions, so it's still very bearable. And yeah, so what else? Yeah, one other thing that I wanted to mention is that our latent space being linear, it's very easy for us to make sure that it's stable at a single attractor point. And we just use a Lyapunov function that is constructed by observing the monotonicity of the value in this space. And then because of the diffeomorphism, we guarantee to have stability in the original space, which is the nonlinear dynamics. Yeah, so these are just images of what we do in robotics. So then we can apply it to represent very complex dynamics. So we're working a lot with things like that, which are a very complex spiral, as we see on the left-hand side. I've lost my mouse again. There it is. They are complex spiral, and we can embed this into a linear space, and then we can control in this linear space for the non-linearities. We've also looked at many different other examples of very complex dynamics, and we can embed that in linear representation. So with this, I want to close by thanking the three key people who worked on this. Bernardo and Aradana worked on the theoretical part with me, and then Stit worked a lot on the actual implementation of the robot. Thank you for your attention. That was a bit long.
This is fantastic. Yeah. So, I mean, I am impressed that you somehow identify Chebyshev polynomials and somehow flatten the problem to put it into a setting where you can actually do quick computations. Now, computing, like, the amount of things you need to do, which is impressive to get it to a point where you can quickly compute, is one thing, right? In the end, putting it into action is another thing. And we do this with the standard robots. We can do actually these actions in a precise manner, because like you compute, sometimes in my head something is dropping and I can imagine just grabbing it, right? But when it comes down to it, you may not have the exact position and so on and so forth. So you not only do the theory, but you can also do the actuators in a way that can do the grasp.
Okay, but that's a different. Okay, so I don't have any slides to illustrate it. So what you're referring to is a very difficult problem. In robotics, indeed, when we control for robots, it's not just planning the trajectory and the velocity. So there exist a lot of controllers where you can be super precise in velocity and position. And so one can just rely on this. And then it's a question of the closed loop control system. So this is to a large extent a solved problem. Here we control directly in joint space. So we don't have what we call the inverse kinematics problem. Usually when you control in Cartesian space, you control for the position and the orientation. So you control for 6 degrees of freedom, but a robot is 7. So then you have to find a path for the elbow to go. And one issue in robotics is often that, if I want to go from this point to the opposite, which I actually cannot do, in space they're very close to one another, but then I have to rotate. So because we control in joint space, we solve a little bit this problem. But no, there are lots of other not trick, but there are other issues to be solved in getting the robots to actually reproduce and generate the trajectory on its own. Yet trajectory planning in robotics remain a big hurdle. It's usually based on computing, with optimal control, many different constraints with optimization, and it works well when you have all your time. But we as humans, I always tend to say, I'm sure it was the case for most of you, you didn't know EPFL. So when you came here, you opened the map and then you looked for the path and then you followed the map, right? But if you do that 2-3 times, next time you do it without thinking. And so that's the difference. If you can embed this into a dynamical system control, your closed form, and then you have a solution which you can retrieve for path planning. So this is only giving you the path. The construction of the path, when you're tracking it, that's a different problem. But constructing this path, you don't want to solve an optimization problem each time. This is too long. It's a bit absurd, because why would you search each time for a solution that you already know?
Yeah.
Once you have it, you should be able to store it and retrieve it.
This is fascinating. I think there is an application you may want to consider, which is not exactly robotics control, but maybe for surgeons. You know about cataract surgeries? So, like a surgeon, for example, does this 5,000 times to be able to say that, they are good at cataract surgery. It has this particular motion I wonder if there is some underlying theory like what you just described that is beautiful, that tells you that there is this control that you basically get it just right.
Yeah, no, but you're totally right. In fact, we know that humans do automate the skill after a while. So we do quite a lot of work on modeling human motor control in this way. And,
yeah, very fascinating.
Yeah. But yeah, thanks.
Other questions?
Thank you for interesting talk. I was especially impressed by the demonstration of robot. So in that case, what are inputs to the robot, or
so
like images or
right?
okay.
So we're not computer vision expert, although nowadays we start using more and more RGBD camera. So in this case, if you pay attention, you see those camera on top, and I'll just play it and stop. Okay, it doesn't want to stop. All right, so pay attention that there are markers on the object, and so those markers are tracked by those camera, and those camera run at 250 hertz. So for such a motion, here it's a relatively simple motion. It's not sufficient to just track. You need to have a prediction. Okay. So for instance, for oops, sorry, it's not going in the right direction. So if I go back to the other problem, oops, which is this one, this is the same thing. We also have markers, right? But in order to be able to predict where the object is going to land, we actually threw, I don't have videos here, but because humans are not good at catching this, but they're good at throwing. So we had humans throwing that and tracking the different motion of the object, and then using this as data for training nonlinear regression. So we are essentially predicting Newton, if you wish, and we're predicting the translational and rotational acceleration of the object for a given object. It's very object dependent. We had some transfer across objects, but it remains fairly object dependent. And we use this as a way to do feed-forward planning. So we predict where the object is going to land, and then we decide where we're going to catch it. So there is much more behind this. Here I focused on only the problem of the classification, but imagine that you have this forward dynamics. Then you have to decide where to catch it. At some point, the object is going to fly into what we call the workspace. But my workspace, I need to have a representation of it. For robot, the workspace, when it's catching it like this, the workspace is not just a point in X, Y, Z. It's not in 3D. It's actually also in orientation space. Because like I said, you need to align yourself. So you're usually, in this case, it's 7 dimension, 7 plus 3. So you actually, or you control only the joint space, you're looking for a region where in traveling in Cartesian space that correspond to region where you can catch it. And we represent this with density probabilities. So it's also the machine learning. We have a closed form representation of the density probability of all the feasible posture. So it's a feasibility space. And then we do simply a line search maximum in this. So we have the object traveling in Cartesian space. We have the map to the joint space, and we look to for the densest region in joint space, which means in joint space, that means that's the posture where I have most possible ways in which I can catch it. And I decide that there's going to be D points, plural, because usually there are more, where I'm going to go. And then I start and I go. And as I go, of course, the camera tells me, oh, but by the way, the object is not exactly flying as you thought, because I have this forward dynamics with dynamical system learned from machine learning. You can use neural networks, but they drift. So your prediction is good for only a few samples ahead of time, and then they start predicting something that is a little off. And so you have to constantly correct. But that means you also have to correct because you're already on your way. So I have a few videos, not here, but a few videos that are incredible. I'm even impressed by the robot because it goes there and then it goes up and then it recatches, which I wouldn't be able to do, me as a human. So yeah, that's the advantage.
Okay. Thank you very much.
Yeah.
All right. So this concludes our session. Let's thank Aude again.